Okay, and and then the technical question is how to maintain this history of the stream. So how to store all that stuff here, how to store all those the history you want to keep. Yeah. So that is the question here. If you're talking about time frames, so how to maintain the history of the stream, just technically, what to store. And typically you store snapshots at regular time intervals. So where you say, okay, at that at regular time intervals, you just store the whole bunch of objects that came in recently after the last snapshot you stored. Yeah, and you typically use finer granularity for recent data, so that you have a detailed representation on the storage, and use a coarser granularity for older data to save space and also to somehow account for a kind of damped window model. And there are typically two time frame models available. So the first one is, or not available, there are more time frame models available, but two are very popular. So one is the so-called tilted time frame, or tilt time frame. In that case, you try to align the time axis with some time scheme. Yeah? So for example, with a natural calendar. And then you use this granularity. So for example, you store one snapshot per minute for the 15 most recent minutes. And then after those 15 minutes, you store one snapshot per quarter for the 4 most recent quarters. And then after the 4 quarters, you store just one snapshot per hour for the 24 most recent hours. And after that, you store just one snapshot per day for the 30 most recent days. And after those 30 days, you store just one snapshot per month, and so on and so on. So the whole thing is aligned to the natural time, to the natural calendar. And the number of snapshots you would store in this schema for 1 year would be just 85. If you compare that with, well, you store that the recent data per minute. So if you would store the whole year, one snapshot per minute, you will end up in, well, how many minutes you have in an hour? 60 minutes per hour, 24 hours per day, 30 days per month, 12 months per year. So you will end up in, well, 500 something thousand snapshots in order to store the whole stream, one snapshot per minute over 1 year. And if you do that with this tilted time frame, you see that you are much more storage efficient than if you do the entire thing. So tilted time frame is sometimes a very good idea, especially if it makes sense to align that with, for example, the natural calendar, the natural time schema. If not, then you can take the pyramidal time frame model. Sorry. So that stores the snapshot in levels of decreasing cardinality. You see, you have different levels starting from the lowest one here, and the cardinality, the capacity of each snapshot decreases with increasing level. So you see here that it's a kind of pyramid which you end up with. Yeah, and the size, meaning the number of snapshots, is controlled by two parameters, alpha and beta, which are natural numbers, as follows. So for a new snapshot, first of all, you provided at some time slot, you store that snapshot on the highest level, I, which fulfills the time slot modulo alpha to the power of I equals to 0. Yeah, and if a level contains more than alpha to the power of beta plus 1 snapshots, you remove the oldest one. So the width, the cardinality, the storage capacity of each level is constrained by this alpha to the power of beta plus 1 constraint. So it is controlled by alpha and beta, as said before here. Yeah, so in that specific example, if you have alpha equals to 2, beta equals to 2, you have 2 to the power of 2, which means 4. So the maximal capacity of each level here is 4, and then you have at most 4 snapshots stored, +1, sorry, +1 of course, at most 5 snapshots per level. And the higher the level it gets, the less you have, since it's a pyramid model. Yeah, the maximal height of the whole thing is constrained by log to the basis of alpha of the current time slot. Yeah, so it may grow. Yeah, it will grow actually. And what happens is, since it grows, somehow probability that the current, the more recent time slots or the more recent snapshots are on the lower level here increases. Yeah, so the more the time evolves, the higher the probability that the lower numbers are on the highest levels, which have a very low capacity. So you delete because you have this capacity thing. So you if the snapshots you store go up in the level, then the probability that you delete them because you're running out of the cardinality increases, and the whole thing with this storage here is that most likely you store the newly arriving things down here. So and that is where you keep the things a little bit longer. Yeah. Okay. So yeah, the number of snapshots is smaller than obviously alpha to the power of beta plus 1 times the height, because so that is the constraint of your storage. So that is what you need to store the whole data frames, yeah, that you keep, because each level at maximum has alpha to the power of beta plus 1, sometimes even some less. And how many levels do you have? It's the maximal height, which is log alpha of t now. And yeah, again, the example, if you store 1 snapshot per second for 100 years using alpha 2 and beta 1, that results in only less than 100 snapshots. Yeah? So only 100 snapshots are stored at a time if you want to somehow manage 1 snapshot per second for 100 years. So that is a very, very storage efficient thing. On the other hand, of course, it means that you do not store a lot of snapshots that you may want to keep or may not want to keep, whatever. Yeah. Okay, so that was the introduction, and next will be clustering now. So we set the scene now for processing our data, for analyzing our data, and now we will have a look on clustering data streams, and as I said before, next week we'll talk about classification data streams. So stay tuned.